development team are listed on the slide as well. So I think probably for the entire week you're going to be hearing mostly about packages that do stuff. And they operate at a fairly global level. All the communication and stuff associated with them is kind of hidden under the table, and you don't really have to deal with it. But in the event that you actually do have to write some of your own routines to move data around on parallel machines, global arrays is one of the libraries you can use to do it. So it's an alternative to MPI. We've been around actually maybe a little longer than MPI has been. We're not as well known, but we present. Yes.
Sorry, Bruce. So these slides are not in the USB memory stick yet. We are going to make them available online.
Okay. So if you actually have to move data around, this provides you a mechanism for doing it, and it's a relatively transparent, easy to use library. So I'll talk a little bit about the global arrays programming model and one-sided communication. Then I'll discuss some basic functions in GA. And after that, I can talk about some of the more advanced features that are also present in the library. And then I'll talk a little bit about some of the other libraries that are based on one-sided communication that are out there, and what kinds of stuff we're working on at the present in global arrays, and where we're going. So typically, in parallel computers, you have a whole lot of processors, and each processor has some memory associated with it. And so when you create a really large data structure and distribute it over these processors, there's two ways of going about it. So one is called distributed data, and basically what you're saying is you've got a whole bunch of processors. Each processor has its own particular chunk of memory, and this data structure is, part of that data structure resides on each process. And so when you want to access the data on a particular process, you have to identify which processor owns it and where on the process it is. So the distribution of data is fairly explicit. But in order to access data, you have to identify which process owns it and where it is on the process. And this is the kind of thing that's typically implemented using a message passing communication scheme. So you're basically sending and receiving data. Alternatively, there's something called shared memory, where you have all these processors, there's all this memory, and the memory is treated like one humongous block of memory. So even though it may actually physically be distributed across processors, it's all hooked up in a way that makes it look like just one big block. So when you create a large data object out on this shared memory, any processor can access it at any time. And so this is nice because when you create your, say your large million by million array, or well, probably you couldn't do that, but anyway, your very large data structure, you stick it out on shared memory, and then anyone can grab any part of it. So this is nice from the programming point of view because there's not all this extra decomposition associated with it. Data access is natural. You can keep the problem sort of formulated in the same terms that you started out with. But one of the problems is that even though it looks like a great big block of memory, it isn't really, and you don't have any idea of how the data is actually physically distributed around the system. So you may be losing performance because you keep accessing pieces of data that are located in some sense far away from you and cost a lot to get over to your process. So global arrays is designed to kind of be the best of both worlds. It presents a shared memory-like programming model to the user, but it supports physically distributed data, and it'll also allow you to probe where that data is. So instead of having to decompose the data accesses into these processes and location on processes type computation, you can just access it directly using some kind of a global index and say, in this example, the matrix element 4.3, which is part of this big distributed data structure, instead of having to figure out that it's on process 2 and it's located in some buffer someplace. So global arrays is built on the idea of one-sided communication, and so to differentiate that from something like MPI, which is based on message passing, message passing is the idea that you have one block or one process that wants to send data and another process that wants to receive data. And so in the program, you have to actually post a send and post a receive in order for this transfer of data to happen. So two processes have to participate in this data exchange. One-sided communication is different in the sense that one process decides that it just wants some memory or wants some data, and it basically goes and either reads that data directly from some other process's memory or overwrites some other process's data without the other process having to having to do anything about it. So you just basically go out and either read some other guy's memory or overwrite his memory. And so this turns out to be a lot easier to program because you only have one process that's determining what the data exchange ought to be. It's a little more dangerous, however, because if you happen to overwrite some other guy's data while he's still using it, you're going to cause problems. So it's simpler to program the data movement, but you have to be a little bit more careful in the sense that you have to manage data consistently in a much more explicit way than you would with message passing. So, as I already mentioned, global arrays uses one-sided communication. The one-sided communication supports the creation of what's called a partition global address space, which just means that you can refer to your data as like just a big array using a global set of indices instead of having to refer to it as, constantly do these decompositions into processors and locations on processors. So this actually makes your programming task a lot easier. And in a lot of cases, you can really simplify programming quite a bit. In parallel programming, usually the first step you take when you got a serial code, you want to go parallel, or at least the first step a lot of people take is they'll go to something called replicated data. And that's where you basically take all your data structures. They're still replicated across all processes. And what you do is you just divide up the work at some place in the code. So the data is replicated. The amount of memory you need per process doesn't change at all, no matter how many processes you have. So that puts an upper limit on how big a problem you can run, and you just divide up the work. And so, preserving the global index space, but allowing yourself to distribute the data actually kind of gives you a way of parallelizing code, distributing your data that isn't a huge step beyond this relatively simple algorithm of replicated data, but it gives you much better performance in both memory and speed because instead of just replicating these huge data structures all over the place, you can actually distribute them. So when should you use message passing and one-sided communication? So message passing is going to be good if communication patterns are regular, at least predictable. Predictable is probably almost a requirement for using message passing. So things like, say, you have a finite difference code that works on structured grids. The communication is going to be tends to be nearest neighbor, and so that's a very regular communication pattern. That works well with message passing. Algorithms have a high degree of synchronization. That means there's a lot of parts of the calculation are locked to each other. You can't do something before something else happens. And then data consistency is straightforward in the sense that if somebody's sending a data, that presumes that he's done modifying it, and if somebody's ready to receive it, the buffers that he wants to receive it into are not being used for anything else. So one-sided communication is good if your communication is irregular. You don't know who's going to be communicating with who. This can happen if you have like dynamic load balancing algorithms. The algorithms are asynchronous. They don't have to happen in any particular order. It works well with many synchronous algorithms, but asynchronous is definitely a plus. But on the other hand, you have to manage data consistency, which means that if you have somebody else overwriting part of your data, then you have to be sure that you are not using that data when that happens. So that kind of thing now has to be explicitly managed by the user. So the global array libraries, it provides a shared memory model in the context of distributed dense arrays. It tends to be much simpler for message passing for a lot of applications. There's a complete environment for parallel code development. Global arrays is completely compatible with MPI, which means that if you have global arrays in part of your code and MPI in another part of your code, that won't cause any problems. This is particularly useful if you're using MPI-based libraries such as Hyper, PETSI, ScaleIPack, you name it. Data locality control is similar to distributed memory message passing, so you can actually figure out which data belongs to you personally and therefore is local and therefore is easy to access versus data that's far away. The library is extensible. You can add new things to it, and it's scalable. It scales to a very large number of processors. It's been used to run codes on 200K cores and more. So core capabilities, it's a library like MPI, so you basically link to it and you call out of it. That's different from some other parallel communication programming models that are more compiler based. It supports dense arrays to 1 to 7 dimensions. In Fortran, it supports 4 data types: integer, real, double precision, double complex. I think in C there's also a long data type. So maybe a couple extras. It provides a global rather than a per task view of data structures. And you have a lot of control over how the data is distributed. Yes?
Is this real? I mean,
Single precision. What?
I mean, what do you mean by the real data type?
Well, there's integer, and in Fortran there's a 32-bit real data type or floating point data type. Yeah. Or sorry, single precision. Wait, this would be. Yeah. I think there's also a single complex. So you have a lot of control over data distributions. How much data gets assigned to each process. There's a lot of collective operations, so things that you can do the entire array like scale all the values by some value stuff. And basically a complete set of one-sided put, get, and accumulate operations, and also non-blocking versions of it. There's also some interfaces to other third-party parallel numerical libraries. I think probably the most useful one at this point, pigs and Summa, or pigs and Tau. I don't know whether anyone uses those much, but ScaleIPack is really useful. And because you have a lot of the GA, when you create a GA, there's already a lot of information available about the distribution and stuff. So it allows us to write wrappers on top. That's basically, you can just, if you specify 2 global arrays and say you want to do a LU decomposition on them, it's just a single line call with 2 fairly simple arguments as opposed to working your way all the way through the ScaleIPack routines. So there's language interfaces to Fortran, C, C++, and Python. We have interoperability with MPI and MPI libraries, so things like PETSI and Hyper. There's explicit interfaces to other systems, so things like ScaleIPack. Pigs is kind of an old, at this point, parallel eigensolver, and Tau is an advanced optimization package. Yes?
How do you do the Python wrappers?
Python wrappers, I really don't know. That's our Python expert is Jeff Daly. So, yeah, I mean, he's actually spent quite a bit of time on it, but I don't know the details of that. I think he used like one of those Fortran or kind of Fortran or C to Python type things.
It looks like it wraps the C API.
Yeah. Well, GA is all written in C, and then all the interfaces are built on top of that. In fact, yes.
What is that interoperability with PETSI?
Well, interoperability just means you can use PETSI calls and GA calls in the same code. There's no interface there's no direct interfaces between the two, but because the MPI libraries are completely interoperable with global arrays, you can have libraries built on either one, or you can have libraries built on MPI incorporated into GA code without running into any difficulties. So here's the actual structure of GA. I'm not sure if any of these well, I guess Threads and maybe Lappy still exist. But anyway, so down at the bottom, you have your network, and the guys that built the network will supply you with libraries that allow you to control the network. So these are the system-specific interfaces. And then on top of that, most of GA is built on top of this ARMCI library, which is mostly written in terms of these network interfaces. But we also use some functionality from MPI for things like global operations, stuff like that. On top of that, there's the actual GA source code itself, which is where all the functionality for GA exists. And then on top of that are these language-specific bindings, so for Fortran C, C++, and Python. So this is where most of the functionality exists. And because we use the MPI runtime, or at least one of the options for building GA is to use the MPI runtime, and that allows us to have compatibility with MPI libraries. So as far as installing GA, we went to an autotools build with GA 5.0. So it's kind of a configure or make install type thing. Usually variables are required. You do have them, so you can provide additional levels of control when you can. Usually GA defaults to a socket. So if you want to access the high-performance network on your system, you have to actually specify which one it is when you configure. So with something like InfiniBand, you'd specify configure -- with OpenIB rather. Most people build GA with MPI, but there's also this TCG MSG runtime that's kind of an ancient thing from Argonne that you can also use to build GA, although at this point we probably wouldn't recommend it if you can possibly get away with not using it. So now that's kind of an overview of GA and the one-sided programming model. So I'll talk a little bit about the basic functionality of GA. This is mostly the functions you use to write just a basic global arrays program. So we have 2 calls to initialize and terminate the library. There's some basically some kind of system configuration information. So the GAN nodes is the number of nodes that you have available to do work. GA is kind of the equivalent of an MPI rank. So it's a process, or it's a number that's going to run between 0 and 1 minus the total number of nodes that uniquely identifies your process. GA create and GA destroy are routines that allow you to create global arrays or destroy them. And get are one-sided operations that allow you to copy from to a global array. GA sync is so flush understanding communication from the system, and it can be used to manage data consistency. GA distribution will tell you which block of the global array is local to your process, or actually it'll tell you what block of data any process owns, but usually it's used to find the data on your process. And then access is a way of directly accessing the process. It's doing it, but if you block a data that you just want on with a library call. So initialization in terms you can use a initialize if you want to a certain extent. And GA terminate the library. Simple world type. Every subroutine has to have some header file. This is just boilerplate. Some declarations and definitions. Initial routine in this case is, and then you initialize, determine application run. So, and this thing on 16 users, you'd see 60 on it. A little more complicated program is to find out what your environment looks like. So in this case, same kind of program, except now we're going to find out how many processes are available and what my process rank is. So we now include these two calls to GA node ID and GA end nodes to find out how many processes and what my rank is. And if you run this on, well, in this case, 4 processes, you get some output that looks like this. Now, usually, if you just have a whole bunch of processes writing to output, there's no guarantee that the order is going to come out in anything sensible. So you'd see something like this, where the ordering is going to be, whatever. But you should see, if you have 4 processes, you should see 4 lines of output. So for creating global arrays, there's lots of ways to create global arrays. This is the easiest way to do it. It's just a single function call. So after you created a global array, you can refer to that using an integer that basically there's an integer handle that corresponds to that data structure. So in a kind of an object-oriented way of thinking about things, this would be like creating an instance of a global array, and then any method that you call would have this global array, or any subroutine in the library that has this global array as a handle as an argument would be like calling a method on an instance in an object-oriented sense. So when you create a global array, you have to specify what type of data it is: single precision, double precision, integers, whatever. How many dimensions the global array has: 1, 2, 3, up to 7. What the extents of each of those dimensions are. You can give it a character string name. And then this chunk array is something that you can use to force the minimum dimension of a local block to be some size. So if you set this to 0 or -1, it just basically, you're completely allowing the library to figure that out. But if you set it to a positive integer, then you're saying basically, when you distribute this data across processes, don't make any individual block less than this size. And this is actually kind of a quick and dirty way of, if you want to force the library to not distribute data along a particular dimension, then if you set that corresponding chunk dimension equal to the size of the array dimension, then it'll prevent it from splitting it across that dimension. So if you wanted like a one-dimensional distribution of data, decomposition of data, that's an easy way of doing it. Character string. Character string is just you give it a name that's array A or something like that. So it's just a ASCII string of characters that describe that array. Yes.
Also put in like your own structs like that.
Well, so instead of using a defined type, yeah, it's. So as long as you're okay with the idea that the structure are all the same size.
Okay, so as long as there's no dynamic allocation.
Right. So if you want to create an array, at least you can do it in C. I mean, we've got the functionality there. What would happen in Fortran? I don't know. But anyway, you can in C for sure. You can basically create a new data type and say, okay, now I want to create a chunk of. I want to create a global array with that data type, and so it'll create a global array with that much memory allocated to each of those elements, and then it's kind of up to you to manage it from there on. But they all have to be the same size. Now we do have a new thing coming out called global pointers that you can create a global array and you can put any size structure inside any element you want. So that's one way of creating global arrays. Now, there's lots of properties you can assign to global arrays. To global arrays themselves. So, and it used to be that for every kind of combination of properties, we had a different create statement, but it was getting unmanageable. So now what we have is this new interface where you create a handle, and you just get an integer back, and so then you can set various properties on that handle. So here, GA set data allows you to define, what data type it is and how big it is. You can set the array name. You can set the chunk. So these are all different individual operations. Now, irregular distribution is a way of decomposing the data in a non-uniform way. If you want to do that, you can add ghost cells to it. You can use a block cyclic or a scale APAC type data distribution. There's a couple others at this point too. And after you assigned all those properties to the global array, you allocate it. And at this point, the global array actually exists. There's actually memory associated with it, whereas before, you're just adding properties to it. So if you were looking at the equivalent of the statement I just showed you before, you call create handle, you call set data, you call set array name, you call set chunk, and then you call set allocate, and that would be about the equivalent. So once you've created a global array, you may want to grab data from or a piece of data out of it and copy it into a local buffer. And so the command for doing that is the following. You have this GA get call. So you specify which GA you want by specifying the handle. You specify what the block is by specifying these low and high indices. So these are basically arrays with whatever the dimension of the or global array is, entries. So if it's a two-dimensional array, each of these buffers has 2 entries. And they're just integers to specify the low and the high corners of the block of data you want. Then there's a buffer that you're going to pass to it, which is just a local array. And there's an array of strides, which says how that buffer is laid out, what the physical dimensions of that buffer are. So what you have is this block of data in a global array gets copied into a local buffer. Now, just to contrast that, if you're doing something similar in a message passing sense, what you do is you have a loop over processes, and this you'd have to run this loop on every process in the system. You have a loop over processors. If me equals PN, then you pack the data into a local message buffer and send the block a message to, so assuming that P0 is where you want this data to end up, send it to P0. Else if me equals P0, then you receive the block of data from wherever it's, yes?
If the buffer is declared, let's say by mistake, but in a different data type, as against the one that you have used for allocating the
global array,
then will it type trust it, or will it?
Well, what'll probably happen is, so it's, it's not going to work out very well for you. It's just, no, not at all. So what it'll do is the low-level routines in GA are basically just saying, okay, here's X number of bits that I have to move from here to here, and it'll go do that. And it doesn't have any mechanisms for saying that the bits over there are supposed to represent a bunch of floating point numbers, and the ones over here are a bunch of 64-bit integers, and it'll just move them, and if they fit, nothing will happen bad for a while until it tries to access that stuff and finds out that there's just garbage in there. So, there's no, yes.
Is that the blocking operation?
No, it isn't. Well, okay, so. Take that back. Okay, this is get is a blocking operation in the sense that you call get and then when you returns, the data is in the buffer and it's ready to go. There's a non-blocking version of it that you call the non-blocking get, and until you call wait, there's no guarantee that the stuff in the buffer is any use whatsoever. Put is, I guess, also a blocking operation in the sense that if you, so put is just basically the same operation, go in the opposite direction. So put, you have data in the buffer and you're putting it out in the global array. And so when you call put and it returns, then that means that the data in that buffer is now someplace out in the network and you can use the buffer safely. It doesn't mean that it's arrived at the destination. So I guess that's the word there. Now, again, if you use a non-blocking put, it'll return immediately, and there's no guarantee until you call wait that it's safe to touch that buffer because the data may still not have been injected into the network. So anyway, so you, I guess so you finish off this loop, you get to the bottom, you still have to probably copy this one last local piece that's local to P0 into your buffer, and you're off, set to go. So this is the kind of thing you'd have to do for this kind of operation in a message passing context. So it's always faster to move data. If it's already on your process, it's going to be much faster to access it than if it's not on your process. And so one of the things you want to know is what data is actually on my process. And you can use this NGA distribution function to learn that. So you specify which global array you want, which process, which is usually my process. But if you want to know what the next process, what block the next process has, you can do that too. And it'll return these low and high indices. So those will be the corner indices of the block that's local to your process. If you want to directly access data, so when global arrays when the library creates an actual global array, I mean, there's a chunk of memory that has a block of that data sitting around someplace, and your process actually has memory out there that's, it's just memory. So if you want to access it directly and operate on it without having to use a put or a get operation and copy it back and forth to local buffers, then you can do that by grabbing a pointer to it. So this is a C interface. There's a Fortran interface that involves like getting basically a memory offset and copying it and using that in a kind of a hokey way to access local data. But you can do it in Fortran as well. And so typically what you use this information for is to partition your calculation and stuff that's local and stuff that's remote. And you want to maximize the amount of local computation you do and minimize the amount of remote data that you need. So the overall model for computation in global arrays is that you have this large distributed shared object. You grab pieces of this and copy them into local buffers. You do something to it. And after you're done with it, you'll copy it back into either the same or a different shared object, usually a different place. And so there's this cycle of, copying data to local buffers, doing something to it, and copying it back to another shared object. At some point, you have to make sure that you're sort of done with some phase of the calculation. All the communication in the system has been flushed out. So at this point, you can say, OK, I know what that data is. So this goes back to this idea of data consistency. And the main mechanism for managing that is this GA sync operation. So GA sync does two things. When you call GA sync, all processes have to get to that call before any process can go past it. And the other thing is all outstanding communication in the system has to be flushed out. So you can say for sure that a global array is in a specific state when you call this synchronization call. And so this is how we manage the idea that if you've got a global array and you're copying data into it, at some point you can say, OK, everybody's done modifying this global array, and now I can safely assume that it's in a specific state, and I can use it, say, as a source of data for the next phase of computation. So an example of just using global arrays on a simple calculation, it would be a parallel matrix multiply. This isn't a very good one, but it does work. So you have two global arrays representing matrix A and B, and you want to multiply them together into matrix C. So you could try something where you do, basically you have this row block and column block. So you grab the row block and column block, copy them onto your process, do just a serial matrix multiplication. You get the product matrix, looks something like this, and then you can just copy it back into the product global array, and you're done. So that's simple. It's not terribly scalable. It's not a real smart algorithm. A better one would be to do something where you divide the system up into smaller blocks, and you grab smaller blocks into your local buffers, do parallel computation. Now, because there are going to be multiple computations contributing to the same block in the product matrix, instead of using a put, you use something called accumulate, which is kind of like a put, except instead of copying over the contents of the buffer into the global array, it adds the contents of the buffer into whatever's already there. And this is an atomic operation, which means that when one process is copying or accumulating the data into a patch of global array, no other process can do it. They're all blocked from doing that. So what that guarantees is that whatever order things happen in, you'll get a consistent answer at the end, because nobody can you can't have two processes simultaneously trying to write to the same location. So the actual code for doing something looks like this. The first thing you do is you find out which block process which process or which block of the product matrix C my process construct the limit block. Use copy the and this is just basically doing the multiplication. You do a local transpose, and then you do the actual matrix multiplication. And when you get the answer, you copy it back into the product matrix. So you get some stuff from A, get some stuff from B, and when you're done, you put some stuff back into C. So that's about all there is to it. So these algorithms tend to, they're pretty simple. So of course they don't have great scaling properties. If you really want to get a matrix multiply that actually performs well, you can use these non-blocking communication, which is pretty much exactly the same as the blocking communication. The only difference is that in addition to all the arguments you had before, you have this one extra argument, which is this non-blocking handle. So if I call this operation, it'll return this non-blocking handle. And until I call this wait operation on the handle, I can't make any assumption that the data in the case of a get has showed up, or in the case of a put that has actually been injected into the network, and I can use the buffer. But what this does allow you to do is, because these, at least if you have non-blocking capabilities in your system, so there's some hardware and library dependencies or operating system dependencies on this capability that have to be there. But if you actually have non-blocking capabilities in the system, then this routine will return immediately, and while the actual communication is going on, you can do something else. So you can overlap communication with computation, and this kind of latency hiding mechanism allows you to extend your scalability frequently quite a bit. So an example of something that would use this is this summa matrix multiplication, where you divided the matrix up into a whole lot of small blocks, and you created two sets of buffers locally. So what you do is you start filling up one buffer, and then you start filling up the other buffer. So usually what you do is the first set of buffers that you fill up, you try and arrange that so that that's just purely local data that's being used to fill these up. So this will happen really quickly. Then you start the calls that'll start filling up this second pair of buffers. You go back and you do the computation on this set of buffers, copy it back into the product matrix, and start up another communication, another call to start filling up this buffer. Then by the time you're done with that, you can call wait on these buffers. Hopefully the data is already there. The wait happens really quick, and you start doing the operation here. So you basically keep kind of filling things up and switching buffers in a way that interleaves the communication with the computation. And so the product or the effect of that is that the communication cost, which normally is something that's sitting between communications, and now overlap with them, and hopefully you don't see that. So this is at this point an absolutely ancient figure, but it does show you the kind of speed up you can get out of this. So this is a comparison with Scale-It-Pack, which is just using MPI kind of blocking communication because of this is the Scale-It-Pack, and then because of the non-blocking stuff, you can actually push up the scalability relatively significantly. Parallel blast. Oh, okay. Well, / scale it pack. PDGM. Oh, okay. I can blame Mano. It's just no longer part of the project for everything. So these are just some recent applications. Scale blast is a genomics application. It basically looks for sequence alignments or something like that. Inspire is kind of an information mining or a data mining application. Smooth particle hydrodynamics is a Lagrangian-based fluid flow solver technique. Stomp is a subsurface hydrology code. And then we have there's a hydrodynamic simulator Tethys that also uses GA. Some other actually, another really useful functionality in GA is something called read increment. So one-sided communication is really good for asynchronous kinds of applications, especially those associated with load balancing. And one way to create a highly load balance or create a load balance code with a lot of asynchronicity in it is to decompose your application into a task. Where each process is going to execute some chunk of work. Or actually, sorry, let me rephrase that. So the application is decomposed into chunks of work, and you can map, say, some integer index to each chunk of work. So what you can do is create a global counter using this read increment function that basically allows any process to access this counter. It'll get returned an integer. Each process or each integer will only be read by any one process, and all integers will be read at least once. So this is a kind of a global counter. You can just go say, okay, I'm done with whatever I was doing. Give me the next task. I'll get this integer back. I'll map that onto a chunk of work. I'll execute it, and when I'm done, I go to the next one. So if somebody has some task that takes a really long time, the work that they might have gotten, they might have been doing, had you just partition this, in some fixed manner, will be picked up by other people that finish their stuff more quickly. So the way to do this is you just create a one-dimensional array with only one element in it. You zero the element out at the start, and then later on, when you call this read increment function, it returns an integer with this property that all integers will be read once and only once, and no integer will be read, and no integer will be read more than once. So one area this is used a lot is in quantum chemistry calculations, which have a ton of asynchronicity associated with them. And quantum chemistry is kind of the flagship application for global arrays. It's what global arrays was originally built to do. You have this Schrodinger equation, and you expand the solution or you assume that the solution is a single Slater determinant, which is kind of a determinant of functions. Each function is a linear combination of basis sets, and you end up at the end of the day with this self-consistent matrix equation where this density matrix is a product of the coefficients appearing in this expansion. And the Fock matrix is this big, huge sum over these 4-index elements. So the bottom line is you have this huge 4-index sum that you have to do with all this work. And so one of the things you can do is to divide this 4-index sum into a bunch of blocks of work. So each block corresponds to some subrange of indices. You have some known number of tasks that you have, so you set up a counter. Each process can read the counter, decompose that into a block of work, do it, and then accumulate the results back into the Fock matrix. So a lot of the quantum chemistry calculations are built around this kind of decomposition of a large high dimensional loop over indices. And so this isn't a Hartree-Fock calculation, but it's kind of a higher level calculation. And using these kind of techniques, people were able to get calculations scaled to hundreds of thousands of processes. So let's see, I'm almost out of time. So, in the notes, which I guess are available or soon to be available, you can look at some of the other functionality in global arrays. We have process groups, which in MPI would correspond to being able to run calculations on subcommunicators in the system. It allows you to kind of decompose your complete set of calculations into multiple kind of subgroups where you can run relatively independent calculations on each subgroup. This can be useful for a lot of things like sort of task-based calculations where you have multiple simulations, so Monte Carlo sampling type things, numerical evaluation gradients. But more recently, looks like there's some interesting applications in things like multiphysics, where you have basically separate simulations kind of coupled to each other. We have some functions that support sparse data manipulation. So a lot of sparse data structures basically in the end boil down to dense one-dimensional arrays. And so we have some routines that can help you manipulate one-dimensional arrays associated with sparse data structures. We've also recently, so this is another data distribution mechanism. We have some functionality that allows you can create a global array that's visible to the entire system, but the data itself is restricted to just a few processors. And it turns out so far nobody's really used this aspect of it very much, but the other thing it allows you to do is to remap which processors have which data. So originally, basically, if you the standard mapping for a global array tends to look something like this. It's kind of column major. So if you have say you have a computer which has 4 processors per node, and you want to kind of arrange it so that there's more spatial locality of the data on a node. So normally, what you get is if you had 4 processors per node and four nodes, for 16 processors, you get a global array layout that looks something like this. You can use the restricted arrays to remap it so the data looks something like this. So you have more compact data layout per node than you would normally. And this has also been used for things like creating fault-tolerant applications as well, where we use this capability to make copies of data, but the data is remapped to processors in a way that if one process goes or one node goes out, there's a copy of that on a different node. We also have some support for different kinds of block cyclic data distributions. So I think Osni has already probably talked a fair amount about it, but one of the distributions that we support will allow you to map directly to the distributions using scale-up packs. So if you're using the GA, if you create a GA with this block cyclic distribution and access a pointer to it using the access functions, you can feed those directly into the scale-up pack routines without any remapping of the data. And what's nice about this is that it's relatively transparent. So the put and the get functions all just operate the same, and they'll figure out all the data decomposition under the hood that you have to do in order to split up the, basically if you just have a big block of data and you put it into the global array, the library itself will figure out how to split everything up into smaller chunks and distribute it properly. Ghost cells are another functionality. If you have some kind of finite difference, finite volume calculation on a structured grid, typically you have to pad the boundaries of your simulation domain with some layer of grid cells. And so global arrays has some mechanisms for doing this automatically, and there's an update operation that will automatically fill in the data from neighboring grid cells into these boundary cells. Well, I don't want anyone to ever know about this resonant arrays. So people keep using it. It depends a lot on how good your parallel I/O system is, whether it's actually going to work or not. And they keep writing in with complaints about it that I have to fix. So. Okay, so some related programming. So let's see. So I'm just going to talk a little bit about some of the stuff we're working on. So just some related programming tools that are co-array Fortran. So this supports distributed arrays. It also supports one-sided communication, but it doesn't really support the global index space. It's still kind of got a per-task view of data. UPC is similar to GA, but it's only available in C, and it doesn't do such a great job with multi-dimensional arrays. So both of these, there's a lot of high-level functionality like matrix multiplies and dot products and stuff like that in GA that tends to be missing in these kinds of libraries. As far as some future work, right at the moment, probably nobody cares about this except us, but we're completely reworking the ARMCI layer inside GA. It's been around for like about 18 years now, and it's pretty crufty. So we're cleaning it out and just revamping it. We're trying to continue to maintain scalability to 100K plus processors. So we want to be able to run on the biggest machines available. We've been doing a lot of work with fault tolerance. We actually have some fault-tolerant applications out there. We've also, at the moment, working on an MPI two-sided port. So we have a couple of versions of GA. You can configure GA to run on top of MPI in a couple of different ways. So usually the best implementations run directly on top of the native libraries, but to increase, in case we don't have a native port, we've been working on some MPI compatibility ports. And so the bottom line one, the one that we're hoping will work on just about any machine that has an MPI library running on it, which is pretty much all of them, is this MPI two-sided port. It isn't very high performance, but it will guarantee that GA runs on just about everything. We're looking at integrating GA with performance tools. I think we already have we've already integrated it with things like Tau, and we've got somebody working on integrating it with HPC Toolkit. Global pointer arrays is a new functionality which will allow you to create global arrays or global array type things that where each array element is some arbitrary data object. And then we have a couple of other activities in energy optimization. So one of the concerns about going to the exascale is that if you build this humongous computer, nobody will be able to afford the energy bill to plug it into the wall. So I'm looking at using adding things directly to the libraries that will help you to support more energy efficient execution of your algorithms. Support for multi-threaded execution. Data composition, load balancing. We're looking at better supporting hybrid GPU, CPU kind of architectures and things like task scheduling and futures, where you basically are doing a much more aggressive job of moving data to the computation or load balancing the computations and moving the computations to the data. Just to say a little bit about global pointers, since we actually do have at least a beta version or an alpha version of this available. So we've got it running on with a C interface. We haven't figured out what the Fortran interface ought to look like. It's right now it has so when you create this pointer array, and then you have to actually assign objects to each element of the array. So we have a customized malloc that allows you to do that. The reason it's customized is because you have to register the network address of each element. We have implementations of put, get, scatter, gather. So you can, those are things that allow you to move data back and forth between the global pointer array and local buffers. And then we've actually got a relatively severe test code that we've used to make sure all this stuff actually works. So this is just the idea of, here you have a one-dimensional array with all sorts of different objects associated with each array element. And if you use a get, you can basically copy a segment of this into a local buffer and as two separate objects. So the current release is 5.1. We're hopefully going to get a patch out in the next week or two. This has a new profiling interface and some weak symbol interposition that allow us to do more profiling. It has support for the user-defined data types. So if you want to define your own data type, create a global array with your own defined type in it, you can do that now. We have an interface to global arrays implementation of some of the NumPy functions, and we've added the MPI multi-threading compatibility port. So this is another one of these MPI ports that if you don't have a native or sort of a high-performance native port, you can try this to get global arrays working on your system. Overall, the idea has proven very successful. We've been around since 1994. Plan to be around for a longer. It's efficient on a wide range of architectures. I mean, this is a high-performance library. It actually does give you good communication performance. Core operations have all been tuned for high performance. And we're trying to get we were originally designed for high-performance computational chemistry, but we've been successful in supporting a lot of other application areas. So just some more information. This is our home page, so everything you want to know about global arrays is available there, including there's a bunch of tutorials available on that site as well. The platforms we're currently supporting are BlueGeneP, the Cray machines, Linux clusters with Ethernet and InfiniBand. We have these compatibility ports. I think these two are relatively high performing. They're not all that much worse than the native ports. This one tends to be fairly low performing because we're basically, trying to implement a one-sided communication library on top of a two-sided communication library. Is not really the smartest thing to do, but this does ensure that if you have MPI two-sided on your system, you can run GA on it. And then also we have Windows support through Sigwin, and I think that's about it. Just for the hands-on session this afternoon, there's all these function declarations are terribly useful for the exercises. So I think everything you need to complete the exercises is available here, and that's it.
Thank you.
Are there questions for Bruce?
With the ghost zones, so does that mean that you duplicate the data in some way locally so that, because it's...
Whoops. Well, let's see, where are they? So normally when you create a global array, you just create a local block like this. Okay, so when you create a global array with ghost cells, you create a larger block. Now, this subblock in the center is the only thing that's really visible, except under certain circumstances. But if you call an update operation, then basically what happens is those ghost regions get filled in with data from the neighboring process.
Okay.
Looks like this. Okay. And it assumes even if your system isn't periodic, it'll just because every block has ghost cells defined on it, it'll just wrap it around. So it's kind of up to you to figure out. Oh, I don't really need this stuff on the edges or the corners. So anyway, it does this operation, this update operation. Then you have to access the data. There's a couple of ways of doing it, but you have to access the ghost cell data, and then you can just operate on it like do whatever you would do.
Okay. That helps.
Yeah.
Any further questions?
So for the if I pass a pointer, a GA pointer, how do you know how to distribute? that has, I mean, I have, my dimensions, or it's something that I'm going to determine. So how do you know how to distribute that out?
So if I'm using this, if you're using the Scaly pack data,
You mentioned that there's this new
Oh.
multi-dimension array, which I can just, like GA pointer or something.
Oh, global pointers? Oh,
Global
wait a
pointer,
minute.
right.
Yeah, okay. Okay, so what happens is, so the first thing you do is you create this global pointer array, and that's basically similar to what you would do to create a global array. Okay, so now I have this collection of global pointers, and locally I have a bunch of these pointers. So what I do is the first thing you do is you create you malloc some memory for the object you want to put in that pointer, and then you initialize it some way, however you're going to do it. And then there's an assign statement. So you say, okay, I'm going to assign this element to this chunk of memory. So there's and so when you create the global array, you have a block of elements that are local to your process, and they must be assigned by that process. So the chunk of, I mean, under the hood, this global pointer thing is, there's like 3 arrays associated with it or something like that. So when you do this assignment, the assignment will automatically, it'll actually cache the pointer to this, actual object into the global array, and plus some information on how big it is and things like that. So once everybody's done the assignment, then anyone can grab, a chunk of this thing. Does that make sense?
Yes.
Okay.
Is the ghost cells for finite differencing methods compatible automatic load balancing?
Well, I guess it's kind of 2 different questions. So my guess is if you were, so the ghost cells apply to just a big block, right? If you wanted to, load balancing probably implies you probably want to divide things up into blocks that are smaller than that. And so if you were doing something like that, you might say, okay, well, I'll just skip ghost cells altogether. And I will just use maybe get operations to grab blocks of data out of this global array and copy them to the local buffer and operate on them and put them back. So if you, so the ghost cell is a fairly optimized data transfer. But you could imagine, if I just ask, if I'm looking at a global array that doesn't have any ghost cells, and I just ask for this block, I'll get all the ghost cell information I need.
But you could also imagine that if you have something spread over 10,000 processors,
Right.
that a small subset of processors might take a very long time, whereas the other ones are just sort of waiting around.
Yeah.
Is that something that's possible to?
Well, so if you were doing something like that, the way you'd handle that is you'd say, okay, this is what I'd have if I just did the standard decomposition. So what you want to do is to divide this up into smaller blocks, and then you can say, okay, these processes that are kind of overloaded, that are going to take a long time. Since I've divided the work up into smaller chunks, somebody out there will finish first and will grab one of those chunks from me. So that would probably be the way to handle something like that.
So I suggest if you have further questions to talk to Bruce later. Lunch is outside, but before break, we're going to take an official photo. Okay, so photographer is outside.